Today we'll also be looking at the relationship between linear velocity and angular velocity. These are two different concepts, but they have a relationship. In one of our previous classes, we treated motion on the straight line and we explained the concept of linear velocity as the rate of change of displacement. We also treated circular motion and we also explained the concept of angular velocity. So we are going to look at the relationship between these two concepts. Now, let's refresh our memory looking at the circular motion. We have the radius, the angular displacement from point A to B, and the distance is covered, and that distance is called S. So this is the axis. So we can now say that angular displacement is S all over R. That's equation 1. Then we also define linear velocity as V equal to displacement all over time, and this is equation 2. So if you look at this equation 1, it's in the perspective of circular motion. This is the perspective of linear motion. So we want to relate these two equations. So from equation 1, if you make S the subject, S will be equal to theta R. Maybe you will name that as equation 3. So if you now substitute equation 3 into equation 2, we now have V equal to S all over T. That is equation 2. Place of S, we substitute this, theta R. So this is equal to theta R all over T. And we can now write this as V equal to theta R all over T. And theta over T is our angular velocity. So we can now write this as V is equal to omega R. So this is a relationship between linear velocity and angular velocity. So we have a problem here to look at. Calculate the angular velocity of 0.5 meter radius bus tire when the bus travels at 36 kilometers per hour. So what you need to do here is, first of all, you write out the parameters. The radius is given as 0.5 meters, and then the V, the linear velocity, is given as 36 kilometers per hour. But just like I keep on telling my students, you have to, this is a standard unit, this is not a standard unit. You can't work with these two. You need to convert this to standard, that is the SI. And previously we have done a class on how we can do this conversion. So if you are converting from a big unit to a small unit, you simply multiply by that relationship. So in this case, converting from kilometers to meters is simply means you are converting from a big to a small unit. So we multiply. Hours to second is still the same thing. So we can write this as but remember, the formula we are using is V equal to omega R. So where this V is known, R is known. So we can say that omega is equal to V all over R. So, but remember, that we need to convert this. So V is equal to 36 kilometer all over hour. So converting kilometers to meters and hours to seconds, to minutes, sorry, seconds, I'm right. So this is equal to the relationship between kilometers and meters is 1,000 meters is equivalent to 1 kilometer. So we simply say this is 36 times 1,000 all over. In 1 hour, we have 3,600 seconds. So this is 60 times 60. So 10 will cancel this. One of these will go with this. 6 here, 1. 6 into 36, 6. 6 here, 1. 6 here, 1. So this is equal to 10 meters per second. Therefore, V, that is omega, is equal to 10 all over 0.5. And when you divide 10 by 0.5, 0.5 is the same thing as half. So this is equal to 10 divided by half, which is equal to 10 times 2 over 1, which is equal to 20 radians per second.